In this video, we'll talk about geometry of the simplex method. This will help us to illustrate and better understand what exactly we are doing when we perform the simplex steps. We start by defining one of the most fundamental concepts in optimization, which is a convex set. First, we define it algebraically, but it's really motivated by geometry, and we'll illustrate the geometrical meaning of it in a minute. But here is the algebraic definition. We call a set X convex if for any pair of points X and Y from this set, and for any scalar alpha between 0 and 1, we have this combination that we call the convex combination of X and Y also belongs to the set X. So what's the convex combination? It's alpha X plus 1 minus alpha Y. Essentially, it's what we know as a weighted average. All right, so we have the weight of alpha given to X and then the weight of 1 minus alpha given to Y, and we sum these two up to obtain some point in between, as we'll see geometrically. To see what exactly the convex combination is geometrically, let's consider an example. So let's say this is our point X, and there are two coordinates, right? So we have one here and one here. So the point X is given by 1, 1. And then let's look at the other point, which will be, say, 3 and 5. So this is our Y, which is given by coordinates 3 and 5. Let's first consider alpha equal to 1/2. Clearly, it's within the interval 0, 1. So for alpha equal to 1/2, we have alpha X plus 1 minus alpha Y is given by 1/2 X plus Y in this case, which will be essentially the average between these 2 points. All right, so for the first component it's going to be 2, and for the second component it's going to be 3. So the point 2, 3 is going to be the point we are going to obtain. All right. So clearly it's right in the middle of the line segment between X and Y. Now, if I take some other value of alpha, so let's say alpha equal to 1/4, then we'll have 1/4 X plus 3/4 Y, and it will give us the following point. So we have 1/4 of 1 plus 3/4 of 3. This gives us 10/4, right? Which is the same as 5/2. And for the second coordinate, we'll have 1/4 plus 15/4, which is 16/4, which is 4. So we have 5/2, which is 2.5, so roughly here, and 4. So this is the point. It is clear that this point is also on the line segment between X and Y. Here is the line segment between X and Y. Any point on this line segment can be described by some alpha within the interval 0, 1. So the higher is the value of alpha, the more of the weight you give to the point X, and the less of the weight you give to the point Y. So which means that if, let's say, alpha is greater than 1/2, then your point will be located within this part of the interval. And then if it is less than 1/2, then you will be closer to Y. And we saw that when alpha is equal to 1/4, then the point was closer to Y than it was to X. All right, so we have a 1-to-1 correspondence between the points in the line segment between X and Y and the points in the convex combination of X and Y. So essentially, the algebraic definition of a convex combination is the same thing as the geometric definition of the line segment between 2 points. Okay, so and then what's the geometric definition of a convex set? We'll call a set convex if for any 2 points within this set, they belong to the set together with the line segment between them. So if I draw the line between any 2 points in my set, then the whole line segment between these 2 points is going to belong to my set. Once again, geometrically, a set X is a convex set if and only if for any pair of points X and Y from this set, the line segment connecting X and Y lies completely within the set X. Alright, so let's look at some illustrations. Here I would like you to pause for half a minute and answer the question which of these 4 sets are convex and which are not. So using the geometrical definition of the convex set, it's very easy to tell that x1 and x2 are convex and x3 and x4 are not. Why? Because for x1 and x2, whenever we try to look at any pair of points within the set, the line segment connecting this pair of points will always be completely within X. Whereas for x3, I can easily find pairs of points such that if I try to connect them with a line segment, then a part of this line segment will be outside of the set. And then similarly for x4, I can take 2 points like this, and then parts of the line segment will be outside of the set. Here is another a little more tricky example. So in this example, we assume that all colored parts belong to the set that we are considering. So our set X would be essentially the set of all the colored points, both here and here. Well, for this one, it's obvious that it's not convex. What about this set right here? So this will be a quiz question, so I'll let you think about it. Next, we introduce another very important concept, the concept of an extreme point. For a convex set, a point X is called extreme if it cannot be represented as a convex combination of 2 distinct points in X, meaning that there is no pair of points x prime and x2 prime both belonging to X, such that X is a convex combination of these 2 points. Alright, so essentially the point X is called extreme if it cannot belong to the interior of a line segment between any 2 points from our set. Okay, so for example, if we go back to the convex sets that we considered here, and remember we defined the concept of an extreme point for a convex set. So we cannot talk about extreme points of these 2 sets because they are not convex. Let's say for x1, if I look at the point x bar, there is no way I can find a line segment within the set x1 such that x bar will be in the interior of that line segment. It can be an end point of a segment, but it cannot be an interior point of the line segment. Similarly for x tilde here. It's also an extreme point. In fact, any point on this part of the boundary, non-linear part of the boundary, is going to be an extreme point. But let's say if I have a point on this part of the boundary between x bar and x tilde, then that point can be represented as a convex combination of x bar and x tilde, so it's not going to be an extreme point. So essentially the set of extreme points for this set will be all the points on this part of the boundary. Okay, so for this set we have only 4 extreme points, and you see this set is defined by lines. So this is a linearly defined set, which is the type of sets that we deal with in linear programming. This set is defined by nonlinear constraints. Therefore, this is not a type of a set that we would deal with in linear programming. So once again, geometrically, a point X is an extreme point if each line segment completely in X that contains the point X will have X as an endpoint, meaning that X cannot be an interior point of that line segment. Okay, so and sometimes we call the extreme points the corner points, and this makes sense especially in the linear programming context, because these points do look like corner points when we draw the feasible region of a linear program in two-dimensional case. And here is an important theorem that relates the extreme points of a set defined by linear constraints to the basic feasible solutions that arise in the context of the simplex method for linear programming. And look, this set X here is a typical feasible set for a linear program. So we have the constraints written in a standard form, AX is equal to B, and then X is greater than or equal to 0. So you'll have X bar as an extreme point of this set if and only if it can be represented as a basic feasible solution of a linear program with the feasible set given by this set X. Okay, so essentially what this means for us is that when we go through the simplex iterations, we essentially go through these corner points of the feasible region. We jump from one basic feasible solution to another, meaning that we go from one corner of the feasible region to another, and then in the end we get a corner that is optimal. Let's consider a two-dimensional example. So here we have the heavenly pouch LP that we have previously solved both geometrically and using the simplex method. And now let's talk about the simplex method applied to this LP in context of the geometrical concepts that we just introduced. So first of all, I want to show that the feasible region for this LP is a convex set. In fact, a feasible region of any LP is a convex set. So we are going to show it for the general case. In our case, the feasible region X capital is given by the set of X's that satisfy all of these inequalities. But in general, the feasible region X would be given by the set AX is equal to B, X is greater than or equal to 0. So this is after we introduce the slack variables and convert the problem into the standard form. Alright, so how do we show that this is a convex set? By definition, what we need to do, we need to take two arbitrary points, let's say x prime and x2 prime, that belong to x, and we need to show that the convex combination of these 2 points, which is alpha x prime plus 1 minus alpha x2 prime, will also belong to x for any alpha between 0 and 1. Right, so how do we do this? So first, because x prime and x2 prime belong to x, they have to satisfy the constraints defining x, right? So we have ax prime is equal to b and x prime is greater than or equal to 0. So then similarly for x2 prime, ax2 prime is equal to b and x2 prime is greater than or equal to 0. Now, I want to show that the convex combination of x prime and x2 prime also belongs to set X, which means that I want to show that, let's say if I denote this by y, alpha x prime plus 1 minus alpha x2 prime, I want to show that y belongs to x also. Right, so but what does it mean? Belonging to x means that y must satisfy these constraints here, meaning that ay is equal to b and y is greater than or equal to 0. So why is it the case? Let's look at these conditions here expressing the fact that x prime and x2 prime belong to the set X. If I multiply the first one by alpha, and then I multiply the second one by 1 minus alpha, and I add these two equations together, then what we'll get is gonna be a times alpha x prime plus 1 minus alpha x2 prime equals b. Alright, but this expression here, alpha x prime plus 1 minus alpha x2 prime, is exactly our y. Right, so we have ay is equal to b, which is exactly what we need to establish. And then clearly, because x prime and x2 prime are greater than or equal to 0, and y is given by this convex combination of x prime and x2 prime, y is also going to be greater than or equal to 0, so both of these conditions are satisfied. And as a result, we can see that the convex combination of x prime and x2 prime also belongs to the set x capital, and this is shown for an arbitrary pair of points from x. Therefore, this proves that the set X defined by the constraints of a linear program is a convex set. So we just have shown that the feasible region of any linear program is a convex set. And this is actually evident from a graphical illustration here for a two-dimensional case, but it's good to establish it for a general case as well. And we have just done it. Now, when we perform the iterations of the simplex method, we essentially generate a sequence of basic feasible solutions, right? And we just saw that basic feasible solutions geometrically correspond to the extreme points of the feasible region of our problem. We are not going to prove this, but let's try to get some intuition about why it is the case using this illustration here. So our initial solution that we start with is point A, which is 0, 0. How do we start? First, let's write it in the dictionary form. We had z is equal to 15x1 plus 25x2. Then we wrote down the expressions for the slack variables through the original variables. We had s1 is given by 450 minus x1 minus x2, then s2 was 300 minus x2, s3 was 2000 minus 4x1 minus 5x2, and finally s4 is 350 minus x1. Alright, so we set all x's to zeros, and then this gave us the values for the slack variables, our basic variables, right? So first of all, the number of non-basic variables is equal to the original number of variables that we have, which is 2. And then the number of basic variables will be as many as we have constraints, because for every constraint we have a basic variable, so the total number of basic variables is 4 in this case. When we write down the basic feasible solution, we set all the non-basic variables to 0. Okay, so let's see what this means geometrically. If we look at our feasible region, we can see that it is actually shaped by several lines. We call this the defining lines. The first line would be the line passing through the points A and B, then B and C, C and D, D and E, E and F and A. So we have the total of 6 lines, right? Now let's look what are the equations for this line. So the first one would be x1 is equal to 0, right? So then for this line, this corresponds to the second constraint, and this line is obtained by setting the second slack variable to 0. So you could describe this line as s2 is equal to 0. So for this one we had x1 is equal to 0. So then the next line that shapes our feasible region passes through the points C and D, and this corresponds to the third constraint. And again, this can be obtained by setting the third slack variable equal to 0, because this is the line corresponding to the third constraint taken at equality, meaning exactly that S3 is equal to 0. Okay, so then the next line corresponds to the first constraint. This is the set of points where the first slack variable is equal to 0. Then the fourth constraint corresponds to this line. We have S4 is equal to 0 here. And finally, for the last line, we have x2 equal to 0. All right, so all of these defining lines, they were obtained by setting either original variable or the slack variable to 0. Setting a slack variable to 0 is equivalent to saying that we want the corresponding inequality constraint to be satisfied at equality. For example, if we set S1 to 0, then this means that the first constraint will be satisfied at equality. And then if, let's say, we have two slack variables set to 0 at the same time, such as S2 and S3, then this means that we want the second and the third constraint to be satisfied at equality at the same time. And we can see that setting S2 and S3 to 0 defines one of the extreme points in the feasible region, which is the point C, which happens to be the optimal solution. So in order to find the optimal solution in our case, all I need is to know the two defining lines that intersect at the point of optimum. Once I know these two defining lines, I just write down the corresponding linear system, solve this system, and this gives me the intersection point C in this case, right? So effectively what the simplex method does, it goes through the set of pairs of intersecting lines that come from the defining lines that we have given in the constraints, including the non-negativity constraints here. And whenever we set two non-basic variables to 0, this corresponds to picking two lines out of 6 defining lines that will define the corresponding basic feasible solution. So in this example, we essentially proceed by picking two defining lines out of 6 at every iteration of the simplex algorithm. But in general, if, let's say, I had m constraints here and I had n variables to start with, then what we would need to do, we would need to pick n out of n plus m defining hyperplanes, because in n-dimensional space we need n hyperplanes to intersect in order to define a corner point. And for a problem like this, we have n plus m defining hyperplanes because we have m hyperplanes corresponding to the inequality constraints, and then we have n hyperplanes corresponding to the non-negativity constraints. So the total is n plus m, and we need to choose n out of n plus m hyperplanes to intersect. Alright, therefore the total number of possibilities for our basic feasible solution is given by m plus n choose n. And because of this, we can only have a finite number of basic feasible solutions, so we can only have a finite number of extreme points. This is why we can terminate the simplex method in a finite number of iterations, because even if we need to enumerate every single corner in our feasible region, there is still a finite number of them, so we must terminate after a finite number of simplex iterations. Of course, m plus n choose n gives only an upper bound on the potential number of basic feasible solutions, because not all the basic solutions are feasible. For example, if I look at the bases where S2 and S4 are non-basic, this means that S2 and S4 are set to 0, and the corresponding intersection point is going to be J, which is clearly outside of the feasible region. So this is what we call a basic infeasible solution. And such basic infeasible solutions are counted among the m plus n choose n possibilities that we consider here. But clearly, basic infeasible solutions can never be encountered during iterations of the simplex method. Also, not all the pairs of variables can be non-basic at the same time. For example, if I set x1 to 0, which corresponds to this line, and I set s4 to 0, which corresponds to this line, then we can see that these two lines never intersect, so there is no corresponding basic feasible or infeasible solution. But even such possibilities are counted among the m plus n choose n possibilities we consider here, so clearly this is just an upper bound on the number of basic feasible solutions. So we have shown that the feasible region for any LP is a convex set. Then we have seen that the feasible region for any LP has only a finite number of extreme points. This is because we can only have a finite number of basic feasible solutions, and basic feasible solutions correspond directly to the extreme points of the feasible region. And then also the third statement we have here is that any LP that has an optimal solution has an extreme point that is optimal. This is something that can be established by analyzing the two-phase simplex method, and we will do it in the context of the fundamental theorem of LP later. Alright, so let's look at what happens exactly when we proceed with the iterations of the simplex method for our problem. So we started at point A that corresponded to the basic feasible solution given by the variables x1 and x2 as non-basic, right? So we saw that here we have x2 equal to 0, and here we have x1 equal to 0 for this line. So at step 1 we see that x2 becomes the basic variable. So x2 is entering the basis, which means that we increase x2 to some positive value, and then we perform the ratio test to see how much we can increase the value of x2. The ratio test winner will be the second constraint, which restricts our movement in the positive direction for x2. Alright, so as a result we end up in point B. Now the second constraint won the ratio test. It means that the slack variable for the second constraint, which is s2, is gonna leave the basis, and s2 is now going to be equal to 0. And we can see that s2 is a non-basic variable now at step 1, so s2 is equal to 0 in this basic feasible solution. So point B is our basic feasible solution after step 1. Then after that, at step 2, we see that our entering variable is x1. So the x1 value increases from 0 to 125, and this corresponds to moving along this line towards the point C, okay? And then the extent of our move is bounded by the constraint given here, so the third constraint. So the third constraint is the constraint that restricts our movement in the positive direction for x1, and as a result the third slack variable s3 will be the leaving variable. So the third row wins the ratio test, and we end up at point C after step 2. Alright, and we can see that this is the optimal solution. So at point C, S2 and S3, the second and the third slack variables, are the non-basic variables that define this point, and the rest of the variables are basic. And we find this point C, which is the optimal point, after 2 iterations. So essentially we went from point A to point B to point C to solve this problem. And look, if let's say at the first iteration, instead of selecting x2 as the entering variable, we selected x1 as the entering variable, then we would go in the opposite direction. So we would go from A to F, then from F to E, from E to D, and from D to C. So you see, this choice of the entering variable at the initial step defines the trajectory of movement for us in this two-dimensional example. So if we go from A to B, then we'll obtain the optimal solution in 2 steps. But if, let's say, we ended up picking x1 as the entering variable, we would have 4 steps to take before we reach the optimal solution. So what happens during the simplex steps? We move through a set of what we call the adjacent basic feasible solutions, or adjacent extreme points, which we can also call vertices of our feasible region. And we call 2 extreme points or 2 basic feasible solutions adjacent if their sets of basic variables differ by just 1 element. So for example, when we went from A to B, what happened? We had x2 as the entering variable, and we had s2 as the leaving variable. So one variable entered the basis, one variable left, but the bases between A and B, they differ only by 1 variable. When we went from B to C, also we dropped 1 basic variable and replaced it with another. So at every iteration of the simplex method, we perform a swap between a basic and a non-basic variable, and as a result we move to the adjacent feasible solution. So geometrically this corresponds to moving through what we call an edge of the feasible region from one point to the next. So in our example, for every extreme point there are only 2 neighbors you can reach from that point in one simplex iteration. For example, from A you can go to either B or F. from B you can go to either A or C, and actually if you went from B to A, your objective would get worse, but going from B to C is the direction of improvement. So effectively you can go from B only to C, because with the simplex method you never move to a point that's actually worse than the one before. Alright, so but you cannot jump, let's say, from A to C in one iteration of the simplex method, because these two extreme points are not adjacent to each other. A is adjacent to only B and F through an edge of our feasible region. This table here shows the correspondence between the basic feasible solutions for our LP and the extreme points of the feasible region. This column lists the basic variables, but in fact it would be easier to define the corresponding extreme point by non-basic variables, because we know that setting two non-basic variables to 0 corresponds to determining the two lines that are going to intersect at our points. So let's say for point C we saw that S2 and S3 were the non-basic variables and the rest variables were basic variables. So you can see that C has x1, x2, s1, s4 as the basic variables. So S2 and S3 are missing, and these are the non-basic variables that define this point. For point D, the non-basic variables would be the first slack variable and the third slack variable. So it would be S1 and S3 as non-basic, which means that the rest of the variables are basic. So we would have for D, x1, x2, s2, and s4 are basic variables, and s1 and s3 are non-basic, and so on. So we have the one-to-one correspondence between the extreme points and the basic feasible solutions.